So here it is. There we go. Right, I added this little bit in. I kind of said it, but I didn't really write it down. This function only works when the numbers inside the square root are positive. And the range of values are -√5 to +√5. That's why our table starts at these numbers. We did that. And the reason for that is that 5 take away x squared has to be greater than or equal to 0. If you plug 5 minus x squared into Desmos just to see what it looks like, here's your x-axis. 5 minus x squared essentially looks like that. And so the answer is only positive from -√5 to +√5, which wasn't the mistake of yesterday because we did cover that. If you look at the x-intercepts, there's one at 0 and there's one at negative and +√5. If you want the y-intercept, it's still at origin. All of that was exactly as it was yesterday. If you differentiate this function, that was the derivative that I got. It's the same guy. If you find out when the derivative is 0, you find these two guys here and here. When you want to find when it's undefined, it ends up being the two endpoints again. That was exactly what happened yesterday. That's the change. Between here and here, I should have chosen -2. I can't remember what I did choose because I threw it away, but you should have chosen -2. And here you should choose 2. And when you put that into your table, you get a negative number here, a positive number here, and a negative number here. And that gets you the minimum that you needed, and this gets you the maximum. And if you put that guy into Desmos, which I have, I'll now show you, and you'll see that the shape that I just gave you actually does match. It goes down, goes up. And in fact, not only does it go down and up, that there, whoops, is the origin. But I guess that shows you the simplest things can catch you, right? Just a simple thing like not putting the right numbers in here and here. Are we good? But I'll just leave this page. I'll come back to it in a second. I'll just leave this page for a few moments. That way you don't need to frantically write it. You can just go and look at the video, right? And, you know, write down whatever it is you want to, or just read it. So that's all you need to do. And time to move. I'll wait a few seconds. Time to move on. Oh God, a joke just came out of my head. Did I tell you the joke about the Scotsman, the American, and the Englishman who went for a job with the CIA?
No.
Do you want to hear that joke, Vanessa?
Yes.
That's it. Blame Vanessa, guys, if you don't like this joke. She said yes. So those three people, right? Scotsman, Englishman, and an American go for a job for the, to join the CIA. So the first one goes in with the American, and he gets an interview, and they ask him all sorts of things. And then at the end, the CIA guy says, there's one more test that you need to pass, and we'll let you join. The American says, not a problem. What do you want me to do? And he picks up this gun and he hands it to the American. He says, I want you to go next door and kill the secretary. And the American guy says, no, I'm not doing it. No. And he says, look, you're not getting the job unless you do it. And so he says, okay, give me the gun. He goes in the next door and you hear bang, bang. And he comes back in, he's got a big grin in his face. And he says, that was a trick. There was blanks in that gun. You just wanted to see if I would do it. And the guy says, of course, there were blanks in that gun. We weren't going to let you really kill it. And he gets a job. And Englishman comes in and he gets the same routine and hands him the gun. And the English guy makes a huge fuss, but eventually grabs the gun and goes next door. And sure enough, bang, bang, comes back in. The Englishman's big smile in his face. Said, that was a trick, wasn't it? There were blanks in that gun. And the guy said, of course there were. And he gets in. So Scots guy goes in. And he gets the same routine. He gets all the questions at the end. The CIA agent says, well, there's one last test. And he passes him the gun. He says, I want you to go next door and kill the secretary. And the Scots guy says, not a problem, I'll do it right away. And the CIA says, do you not want to argue about it? He says, no, if you want me to kill her, I'll kill her, not a problem. Says he shrugs his shoulder, and so he goes into the next room, and you hear bang, bang, and he comes back out, and the Scotsman's got a big grin in his face and says, that was a trick. There was blanks in that gun. You know I had to strangle her?
That's where I thought it would lead to.
Did you? You're seeing it coming that way? Okay. Right. If nothing else, you've had enough time to copy that if you wanted to. So we are going pretty much picking different situations to sketch using calculus. So the next one, I think I'll use actually their questions. That way there's a good chance that they'll come out relatively nicely. So the next one I'm going to do is fractional powers and how we would deal with that. And where are we? I know there's at least one fractional power somewhere. I saw it a minute ago. Okay, this is a version of question 8. Right, so we want to do a sketch of this function, and we're going to try and get as many features as we can to help us do that, and calculus is going to be part of that. So the first thing I'm going to do is find the x-intercept. And it is not as easy as you think for a question like this, because we have to solve a really weird looking equation. And that means we're going to do some algebra things that are not typical. I'm going to pull out a common factor. Right, that's typically how you would do this. And the common factor is actually x to the 2/3. So you might say, well, why 2/3? Well, if you've got two terms and both have powers of x in them, even if those powers are fractions, you can pull out a common factor. And isn't the rule that when you've got x cubed and x squared, you always pull out the x squared, right? The smaller of the two, right? So the smaller between 2/3 and 5/3 is 2/3. So I pull that out. Now that makes this guy 25, agreed? Now, right, common factor, 25. This is a sneaky one. What do you get if you take x to the 5/3 and you remove 2/3 of a power from it? What's left? 5/3 take away 2/3. What's left?
1.
And x to the 1, we call it x. Do you see how nicely that factored? Now, what are going to be the two places then where you get 0? Well, this one is going to get you x equals 0, and this one is going to give you x equals 25. If I just said to you, when is this equal to 0? Most people would have said, oh yeah, 0 works. Would you agree it would be much harder to figure out the other answer was 25? And that's why factoring is your friend. Now I'm going to go over here and I'm going to start putting things in as we find them. Now, since that's 25, I'm definitely going to have to do a scale. I'm not going to do 25 boxes. I don't even think I've got 25. So how about 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 2, 4, there. You're happy about that scale so I can fit 25 in? Okay, that's fun. Now we're going to differentiate. So start with the original. It's a power rule. Multiply by the power and reduce it by 1, which is basically 3/3. So you get that. You're then going to multiply by the power which is 50 thirds, and you're going to take 1 away from it, and you're going to get that. So multiply by the power, take away 1, multiply by the power, and take away 1. So far, so good. Let's do style points. Let's see if we can factor this. Now, both of them have a power of x, so I know I can pull out a common factor. Is there any number, any fraction I can pull out as a common factor while we're at it? Can you see any fraction that I could pull out as a common factor from those two terms?
5/3.
Agreed. Now, x to the 2/3 or x to the negative 1/3. Which one of those two is going to be my common factor, the guy I pull out? The rule is the smaller of the two. So which do I pull out?
The 1/3.
Right. Now, that is not a normal factoring. Would you agree that's not something you normally pull out as a common factor? Don't you pull out a common factor of x or x cubed or something, right? Nice numbers, positive numbers. But factoring can also include fractional powers, and it can also include negative fractional powers. Now, if you use up 5 and 3 and all of that, are you happy that you get 10? Are you comfortable where that 10 comes when I take 5/3 out of that and I use up all of this? Okay. Now, the weird one's coming up. All used up. 2/3, take away this amount, right? Because it's 5/3, take away 2/3, right? That's how you do it. So I've got 2/3 and I'm going to take away negative 1/2. What do you get when you do that? 2/3, take away negative 1/3.
1.
You get 1. Isn't that amazing? That you can factor something as ugly as that. Now, I'm still on style points. I'm keeping the 5 on the top. I'm going to bring the 3 down, and I'm going to call that guy in the bottom x to 1/3. I'm just trying to make it look pretty. Are you happy with that line? Are you happy with this negative is now downstairs? We've done that algebra before. And technically, I don't need to do this line, but for me, visually, it helps. There we go. Isn't x to the 3rd a cube root? I know I don't need to do that, but it just kind of, I don't know, cube roots look nicer in my brain, but there's nothing wrong with that answer. If you stop there, you're right. If that distracts you, pretend I didn't do that, right? But for me, that makes things a little bit easier. So I have found the derivative. What I need to do is use it to find critical numbers, places where things that are useful are going to happen. So I'm going to find when is the derivative 0, and I'm also going to find when is the derivative undefined. Well, the derivative is this guy. Okay, that's the derivative. Don't overthink this one. If this fraction is 0, doesn't it only happen when the top is 0? We don't care what the bottom does. Now, if you look at that, would you see it's pretty obvious that x equals 10 is the answer, right? So one of our critical numbers is that something interesting, maybe a local max, maybe a local min, something's happening at x equals 10. Great. Now, there is another situation, and that is, when is this derivative undefined? Again, don't make your life difficult. If you have a fraction and it's undefined, isn't it only the bottom that matters? And when the bottom is 0, you'll get undefined. So what value of x makes the bottom 0? Because that's undefined.
0.
0 it is. And we are ready to do our table of signs. Now, in this particular one, there are no restrictions. You know, like the square root, I had to start here and finish here. There are no restrictions. So it's going to be a gap, a 0, a gap, a 10, a gap, like that. And I'm going to be doing the first derivative, and I'm going to do the shape. Here, how about -1? I don't know why, 5, and just because I want to, 11. And I'll now go to my calculator and set up a table to find out what the value of the derivative at all of these values are. So clear this guy out. It's going to be 5 bracket x take away 10, close the brackets, divided by, that's not going to be pretty. I'm going to put a bracket around this and call it 5 times x to the power of 1/3.
Is that denominator supposed to have a 3 instead?
Well caught, thank you. The good news, it had no effect on any of the answers, but it's important that I write the right thing down. So we got that guy. Right, 5 on the top, 3 in the bottom, looks good. Can you see how ugly a cube root is? It's x to the power of 1/3. And there is a button, I don't know where it is because I never looked for it, but there is a cube root button, but it's probably so well hidden it's not worth finding. That's probably why I don't bother anymore. So call it a 1/3 power. Right, I'm now going to second table, get rid of the old stuff, and type in -1, 0, 5, 10, and 11. And let's see what we got. We got 18.3, which is positive. We got an error. Well, actually, an error just means it's undefined, which we knew anyway, right? At 5, it was -4 point something, 4.8. At 10, it was 0. Yeah, we knew that anyway. And at 11, it was 0.74. So I have a positive, an undefined, a negative, a 0, and a positive. I'll draw my little number line thing, and I'll put in my 0 and my 10. Only put in my critical numbers. And here it's 0, and here it's undefined. And on this side, they're all pluses, then it's all negatives, and then it's all pluses. And if I try and figure out what's going on, here it's going down the way, it's going horizontal, and it's going up. So I know for sure that there's a local minimum here. And it happens at x equals 10, and I'll figure out the y value later. Here, it's plus and it's minus. But because it's undefined, it's going to be one of those cusps, you know, those little tops of houses shapes. So technically speaking, isn't that a local max? And that's going to happen at an x coordinate of 0. And I also know what the y coordinate is. So that's at 0, 0. So I'm going to my shape here. And at 0, 0, I have a guy that looks something like this. And at 10 comma, I don't know what the 10 comma is yet. So I'm going to go here and just figure out what it is on the calculator roughly. So 10 to the power of 5/3. Take away 25 times 10. I don't need that bracket. Times 10 to the power of 2/3. I get the answer about -69. So I got a guy at 10 comma. Can we pretend that's negative 69. And what do I know that's happening here? That's happening. So it's going to go like that. It's going to come up and meet that, and it's going to go like that. It looks a bit like a ziggy-zag guy. This here is quite sharp. This here is probably a little bit more curved than I drew it. Let's check it out. I'll do it on Desmos. So when I go to Desmos, here we go. That's our question 7. Putting in the original function again, which is x to the power of 5/3. Take away 25x to the power of 2/3. That scale, I need to go at least negative 10 to plus 25. So I'm going to go here and I'm going to say negative 10 to actually a little bit more than 25. Let's say negative 10 to 30. And the y values, well, definitely went down as low as negative 69. So I'm going to make that negative 80. And what does it climb up to? Ugh. Well, I don't know, climb up to, let's say 20 there. So if I click out all this and shrink back a bit, would you agree that's pretty much the shape I had? Do you see the little cusp at the origin? And that guy there? Yep, you see it? 10, negative 69. Everything matches. But it's also a lot of work, isn't it? Just for one guy. Now, once you've realized how to do these guys, in a real world situation, wouldn't you use Desmos if you wanted to see what it looked like? But now you can look at that and you can say, I now know why that's a funny V shape. The derivative was undefined there, right? And it made one of those cusps. I understand that that's where the local min is, and I know why it's at 10 and not somewhere else, right? Because that's where my derivative says. I also know something that Desmos doesn't tell me. Doesn't this curve not have any more hills or valleys in it, right? It doesn't curve round again. If you only do Desmos, isn't there at least a chance that maybe over somewhere at 500, it might curve back down again, right? It could do all sorts of things. But I know because of calculus that that is all that that shape will ever have. And so I feel good about that. Any questions about that one before we move on to our next one? Okay. Give me a few moments. For some reason, I lost my guy. Well, done polynomials. We've done rational functions. We've done square roots. We've now done a fractional one, which is fine. We're going to do a trig one next. And so this one is similar to question 9. Okay. Whenever you deal with sines and cosines, tans, anything with trig, they are a little bit different than normal curves, whatever that means. You know, when you do a polynomial, it does what it does, but after a while, doesn't it just basically not do anything clever? It just keeps on going upwards and onwards, right? And that happens with square roots and all sorts of things. But when you have a sine function, don't sine functions go on forever? In other words, there is an infinite number of hills and valleys. And even if you do this all that you end up doing is make the sine function kind of go up a hill, right? So when you deal with a trig function, I suggest that you put your own constraints. So I'm only going to do this shape from 0 to 2 pi. Because if I didn't, wouldn't I have to find an infinite number of critical numbers? Wouldn't there be an infinite number else? And nobody can do that, right? So if I stick to that, won't that be like the template? And then once I know what that looks like, can't I just say, well, you just keep doing it again and again, right? So if I end up saying, I can't really draw the shape well, but let's pretend that my shape looked like that, right? From 0 to 2 pi. Wouldn't I just say, well, you just keep doing that? And won't I then understand the whole shape? Right. So when you have trig, restrict yourself from 0 to 2 pi, and then just realize that that's like the thing that repeats for the rest of the universe. So I'll start again. X-intercept ends up being x plus sine x equals 0. That's not going to work. You won't be able to solve that algebraically. So I'm going to go into y equals. I'm going to make sure that I am in radians. This calculus is in radians. I'm going to go set and quit. I'm going to do y equals x plus sine of x. And I'm going to use the calculator then to essentially tell me, where does this function, in the range 0 to 2 pi at least, where does it cut the x-axis, right? So if that was it, it'd be 3 points. Now I'm going to go to my window and I'm going to do 0 to 2 pi. And then I'm going to do zoom 0, which basically lets the calculator figure out a good sketch for it. And when you look at that, would you agree that there's only one x-intercept and it's at 0? That's fine. That makes my life easy. But that's how we figured that out. Now, if you want to get a y-intercept, you can normally get that a little bit easier. It's just the value of the function at 0, which also happens to be 0. So all I've managed to find out from that step is that it crosses the x and y axis at the origin. Okay. That's good. At least I know that. So let's find the derivative now. 1 plus the cosine of x. Now, there are two types of critical numbers, right? Derivatives being 0 and derivatives being undefined. Would you agree that that's never going to be undefined? So I'm only going to be looking for the critical numbers when the derivative is 0. And what means I am going to be looking at solving that equation. Now, I know I've got a unit circle somewhere. Please tell me I haven't thrown it away. We have. Oh, it's annoying. And we can still do it. If you want to solve this equation, aren't you trying to find out when cosine of x is -1? Agreed? In radians, what angle has a cosine equal to -1? So if I had my little unit circle, it'd be here, right? Which angle has a cosine of -1?
Pi.
Agreed. Isn't it the x coordinate is -1? So you nailed it. It's pi. Technically speaking, wouldn't there be a 1 at 3 pi, 5 pi, 77 pi, 2 million and 1 pi? But we're not going to do that, isn't that? Because that means we'd have to do an infinite number of answers. So I'm only going to stick to that guy, right? 1 on. Which means that table of signs is going to be pretty small. We go. Table of signs. Okay, pi is roughly about 3.1, right? 3.14, right? So unlike last time, I actually have found the decimal of that. So I want something a little bit bigger than that guy and a little bit less. Does 4 and 2 seem reasonable?
I would choose 1, but that's because I'm lazy.
Oh, I'm having an influence on you, Rachel. Instead of the word lazy, say I am more efficient. Right?
Yes, that's it.
That's it. Okay. But since I've committed to this, and it's not that horrible a function, I should be able to get it, right? So I'm just going to do 1 plus the cosine of 2. And the answer is 0.58. I already know that answer is 0. And for 4, 1 plus the cosine of 4, and I get the answer 0.34. So I get a positive, a 0, and some more positives. And that's okay, it's actually the right answer. So this shape goes that way. That shape is not a local max. That shape is not a local min. Isn't that a funny one? It's called a horizontal point of inflection, right? Well, here is my shape. If I call this guy here 2 pi, right, and there's my 0, I have it's put pi in the middle. I know it passes through there. Oh, I guess I should find the coordinates of this thing, right? So what's that? Pi comma something. Pi plus the sine of pi is, oh, pi comma pi. Okay. So 1, 2, 3, 4. Pi is about there. And imagine that's 3 and that's 4. So pi is about there. So it's here and it's a horizontal. So it comes up and it goes like that and then it goes up. Now, what's it going to do for the rest of its life? If you imagine that as being a snapshot, won't the shape just keep on going up, flatten off and go up? Then it's going to go here. It's going to go. Can I look like that? Not great at drawing. And trust me, that is exactly what it looks like when you put it into Desmos, if you choose good windows.
I have a question about that one.
Yes.
When you first saw it and you said you can't differentiate it just by looking at it, what was it that made you be able to know that?
Not so much I couldn't differentiate it, but I couldn't solve that algebraically. Is that what you mean?
Yes.
Yeah. Trig only plays well with other trigs. So if that was a sine x and a tan x or a sine x and a cosine x, I probably could have got the answer algebraically. But the minute you start mixing x's and x squares and e to the x's with any kind of trig function, the two never play well together. The algebra isn't going to happen, right? I'm not going to be able to do algebra and get an exact value. The best I can do is plug into a calculator and get the decimals. This one happened to be 0, but in general, the answer is going to be 1.23 and 7.98, right? You're just going to get really ugly decimal approximations. So if you ever see a trig mixed with any power of x or log x or e to the x, basically anything that's not another trig, you're probably not going to be able to get the answer algebraically. You're just going to get an estimate using the calculator.
Okay, thank you.
So here is our next one in our list, because we're darn close. Yeah, we are. Perfect timing. We've got one more question to do, and that will be us covered everything that you need for the homework. So, number 10. And I'm keeping the best till last. This is I guess I would describe it as an exponential in it, right? How do you sketch functions with e to the somebody in it, like this one here? Oh, I don't have any real major problems with this one, you would think. But it's basically got problems everywhere. So let's go for something that should never cause trouble. X-intercepts. Well, I'm looking for when is this guy equal to 0? And you might say, not a problem. X equals 0, surely. Would that make sense? Normally that would be exactly correct, right? X times somebody, X is 0. Not this time. If I put 0 in, isn't that the answer? Right? Now you might say, I don't see a problem. And there might not be, but let's find out. What is 1 over 0? 1 divided.
Permanent?
Well, we do call it that, but in a more precise way, isn't it negative infinity? 1 divided by 0 gets you infinity. Okay. Indeterminate form, but we call it, in this case, we call it infinity. And that becomes 0 over e to the infinity. So let's keep going. Isn't e to the power of infinity just infinitely large? Now, is 0 over infinity indeterminate form, or is 0 over infinity equal to something that we know the answer to?
You said a day or two ago, that's like 0 on steroids.
It is, so the answer is 0. So yes, this particular question, it was 0, but that guy is a problem. I'll tell you why it's a problem. If I just changed the question to be that one, you're going to do E0, e to the 1 over 0. 0 times e to the infinity, you're going to do 0 times infinity. And isn't 0 times infinity bad news for everybody? So we dodged a bullet there, right? So the x-intercept is 0. And by the way, when the x-intercept is 0, doesn't that make the y 0? So we know it is the origin. So we're not going to get an awful lot out of that, but we did get a useful piece of information, and that is that the x and y intercepts meet at the origin. So almost everything we're going to do with this function is going to be awkward. So that guy's done. I now need to differentiate it. This is a product rule. F dash g plus f of g dashed. But it's not just any old product rule. It's a product rule where you have to differentiate e to the negative 1 over x. Would you agree that differentiating that guy is a chain rule? Right? Differentiating e to the negative 1 over x is really messy. When I have questions where things are messy, I do the working at the side. So that guy is x, its derivative, dead easy. Now the tricky one. This guy is g. If you want to differentiate e to the negative 1 over x, you get e to the negative 1 over x, but then don't you finish with the derivative of negative 1 over x. If you had to differentiate negative 1 over x, you would call it x to the power of negative 1 and do it. If you just trust me, it ends up being that guy. So our derivative, right? So if you differentiate this, you get that guy. Our derivative is f dashed, that guy, plus e to the negative 1 over x times that guy.
Should that be a negative 1 over x squared?
It's actually going to be a positive. I understand why you would say it was negative. Let me show you how I would do it. I would call it that guy. Now, when you multiply it by a power, do you see it becomes positive? And then you reduce the power by 1. And so it's positive 1 over x squared.
Okay.
Right? Now, style points. Can you see any common factor? Because common factors are very typical for these questions. Can you see any common factor that this term and that term share?
E to the negative 1 over x.
Correct. And that leaves me with that guy. You agree? Now, I could spend some time on combining those two fractions, and if I did, that's fine. But I'm going to save some time because we're running short of room. This thing here will never be 0. So here's my argument for why 1 plus 1 over x squared, no matter what x I pick, can never be 0. Would you agree that if you take any number and you square it, you get a positive answer, right? 5 or negative 5. You agree you get a positive answer. So won't x squared be positive? So won't 1 over x squared be positive? Can you see 1 plus a thing can never be 0? Convinced you? Right, so I don't need to worry about making it pretty because none of my critical numbers, at least in that sense, are going to come from here. So let's look at when is this guy 0 and when is this guy undefined. So I have, when is this guy 0? And I have, when is this guy undefined? And nothing is pretty about this. Let's do the undefined ones. If you look at this expression, is there any value of x that is screaming out, don't use me, because if you try, the calculation's going to be horrible, it's not going to work? I can see a pretty obvious value of x that is causing a problem with this calculation. Which value of x? I heard it, 0. Would you agree 0? If that isn't 0 a problem here and it's another problem here, right? It's a problem everywhere. 0, oh, is a problem. Now this is less obvious. This guy is never going to be 0. We've already argued why 1 plus 1 over x squared is never 0. Can you trust me that e to the power of anything is never 0, right? E squared is never 0, e to the negative 2 is never 0, e to the 0 is 1. It's never 0, so there are none, which means that we don't have a very big table of signs. And I'm picking 0 in the middle and negative and plus 1, because unlike Rachel, I'm not lazy, I'm efficient. Did you get that dig, Rachel? Oh God, I love this job. Do you know they pay me money to do this? Scary. For insulting students, I get paid money. Go figure. It's undefined. Undefined. I guess I should plug this horrible thing into the calculator, or I could do them separately because there's only 2 of them. I'll do them separately. Right, this fella here. If you plug in negative 1, you get. Make sure it's on. You get e to the power of negative 1. Wait a minute. Let's just be safe here with brackets. E to the power of negative 1. No, you don't. Try it again. negative 1 gets you 1. So it's actually e to the power of 1 times a bracket 1 plus 1 divided by negative 1 squared. And that answer ends up being 5.4. And then if you do a 1, you get e to the power of negative 1 times, in brackets, 1 plus 1 divided by 1 squared. And you get a 0.73. So this guy is positive, so is this guy is positive, and this thing here is undefined. What on earth is going on here? Well, it could be, well, it goes plus and it goes plus, and undefined don't really match that. And so the problem that we've got is that this function here has something really weird going on at the origin. And so I'm going to take my guy negative 1 and my guy 1, and I'm going to find the value of the function at each of these points. So at x equals negative 1, the function is negative 1 e to the power of 1, which is negative e, which puts it down here somewhere. And the value of the function at 1 is 1 times e to the power of negative 1, which is basically 1 over e, which is kind of about there. And now I'm going to find the limit as x tends to 0 of this guy. And the reason I'm doing that is that I'm not 100% sure that this function actually ends up being 0. I'm pretty sure one of the limits are, but not the whole function. If you take this function, you can find the limit as x tends to 0. Okay, very quick. You get that guy? I'm going to do a L'Hopital on him. The top guy gets you e to the negative 1 over x times the derivative of that guy, and the derivative of that guy is 1 over x squared. And the bottom gets you negative 1 over x squared. They cancel out, and you get negative e to the negative 1 over x, and that's the limit as x tends to 0. And so you get you get negative e to the negative 1 over 0, and you get 0. So I definitely know that when you go from the plus side, you get 0. So this function comes down like that. Now, if you make that 0 minus, this guy becomes that fella, which is negative infinity. So that's what was going on. This function was going like that. Go figure. And sorry for overshooting your time. The last bit, to be honest, the only way I could figure that out would be actually going into Desmos, because there's nothing clear about how a function can be positive at both ends. And it's positive at both ends because it goes like that. And then something really weird is happening at 0, and I just did that by limits. I probably could have done it by test points.